Well, welcome everybody. Hello. Um, this is Data Types Do Matter. And quick bit about me. I live in High Point, North Carolina. That is on the east coast of the US. I'm about 4 hours from the ocean. So not super close to the beach. I would much rather be closer, but we have hurricanes here. So we're a safe distance away from the hurricanes. I am a solution architect at Blue Granite. I'm a data platform MVP. I do tweet. My handle is SQL Swimmer. And why SQL Swimmer? Well, not only am I a swimmer, but I'm also a coach and an instructor. And I'm going to kind of take 10 seconds here to get on my soapbox and say, if you, as an adult, think that you cannot learn to swim, you are absolutely wrong. There are instructors who are specially trained like myself, who are trained to teach adults how to swim because it's very different than teaching children how to swim. But I also teach little kids and I also coach little kids. So I have a lot of energy because trying to keep the attention of a 4-year-old when they are freezing cold in the water, I've learned to talk super fast. So if I do get to talking too fast, just let me know and I'm happy to slow down. All right, enough about me. Huge thank you goes out to all of the sponsors for Data Saturday today. Couldn't do it without them, so very much appreciated, especially at this inaugural event. You know a little bit about me. Now I want to know a little bit about you. So are you a developer? Are you a DBA? Are you an analyst? Are you something different? And normally when I do these sessions, we do them in person, but we don't have that luxury today. So if you could put this in the chat so I can see who's my audience today. I would love to know that from you guys. All right, we've got a developer, a data scientist, an analyst. Awesome. We got a really good mixed crowd going here. That's wonderful. Awesome. Oh, developer, DBA, analyst, everything. Yes, yes, that the hat that has many things associated with it. Totally get that one. All right, awesome. Well, what we are going to talk about today is, if I can get my slides to advance, we're going to talk about data types and why they matter and how they can affect your data quality, your storage, and your performance. But before we do that, I'm going to take a quick selfie. If any of you are familiar with me, you know that I always do this when I get ready to do a session. Normally, again, I do it in person with people. But we have to do it this way. And I'm going to encourage you to all do the same thing so I can see your bright, shiny faces. So I am taking my picture. All right. And now I am going to put it out on social media because we all know that nothing really happens in life unless you put it out on social media to make it real. So, all right, that is done. Let's keep going. And data quality, that's the first bit that we're going to talk about today. So SQL Server actually has 30 different data types, and we're not going to talk about all of those today, but we are going to talk about the temporal data type, so your date time to small date time date. We're going to talk about whole numbers, and we're going to talk about character data. And the reason that I chose these specific areas, so I'm a former DBA, and as a DBA, you know, had to do a lot of performance tuning and whatnot. And then I switched over into the BI realm about 10 years ago. And this is where I saw the most, I don't want to say mistakes, but the most misconceptions about data types. And is with these 3 buckets of data types. So that's why I'm focusing on these today. So data quality. Data quality is a huge thing. Who cares how fast your query comes back if you get the wrong data? So we're going to start out by talking about character data types because that's everybody's favorite data type, especially for storing temporal data, your dates and times, or numbers. Now, I will admit, I am guilty of this. I have done this on more than one occasion where I'm trying to import something into my database and I can't get it to work, and I'm using all of the correct data types, and finally I just throw my hands up in the air and say, forget it. I'm just importing it as character data and moving on, and I'll deal with it later. So character data types do save us quite frequently, but we don't want to leave them in that scenario. We want to make sure that we follow up and put them in the correct data type if we do something like that. So let's just take a really quick look at a demo so that we can talk about how your data quality is affected. So I've got my SQL Server open over here, and I just have what I've done is I've pulled a table from the Wide World Importers, the invoices table, and what I'm going to do is I've made a copy of it and I've dumped it into my demo database. And one of the fields in here is invoice date. Let me come over here so you guys can see that. And right now, right there, is right in front of me. If it was a snake, it would have bit me. All right. So I made a copy of that, and I'm pulling in just the salesperson ID, the invoice date, and then what I did is I added an additional column for the invoice date, but I made it a varchar 20 field. And you can see in my demo right here, it's the same data, but I'm storing it as a varchar 20 and not as a date time data type. So let's go through. Now, in the United States, and I think nowhere else on earth but the United States. Oh no, I think the country of Myanmar does this as well. We store our dates month, day, year. Everybody else in the world and probably the universe stores theirs as day, month, year. So for me, when I look at August 7th, 2015, it's 8/7/2015. So I know that I'm speaking to mostly a European crowd outside the United States. So just want to be sure that you understand where I'm coming from on this one. So I'm going to look at my date data type, invoice date field, and get a distinct count for that. Now we would expect one because there's only one August 7th of 2015, and that's exactly what we get. But what happens if we do a select and distinct count on that varchar 20 field when we filter for August 7th of 2015, we actually get 10 records. That doesn't quite jive with what we know. That's I'm not following that. So let's investigate and see what we're doing here. So if I come in here, let's see how many records in our table when we look at the date data type field there are, and there are 62. Well, let's look and see what happens when we look at that varchar 20 field. And look at that, we only have 3. Now, I don't know about you guys, but if I was one of the vendors whose invoices was lost and I never got paid, I would be a little mad because right now we're missing 59 invoices with that invoice date. So our data quality has been affected. Let's dig a little bit deeper. Let's look at the min and max when we look at the date data type. And here we've got January 1 of 2013 to April 30, 2016. Well, let's look and see what we have when we look at that character data. And you'll notice we get completely different answers. And this one doesn't even have a year associated with it. Because I'm storing it as character data, I can put whatever I want. Now, a lot of times people will stop me and ask me, well, my front end, it prevents people from doing that. That's awesome. You should have that in place to prevent that from happening, but you also need to do it in the database layer because there is nothing stopping anybody who has access to your database to going in there and modifying the data. inappropriately. And when I say inappropriately, they do things like this because they didn't know any better. Or if you are working with people who are both in the US and outside the US, and August 7th, that's exactly what shows up on the earliest over here. This is how people outside the US view August 7th. But if you are in the US, that's July 8th. So, it makes a difference. You need to store those data types, that data in the correct data type to prevent something like that from happening. All right, well, so we talked about, well, let's just import it as character data and then we'll convert it later. Okay, well, we've got the ability, we've got a convert function, and let's see what happens. Well, we get this big red ugly message that says, yeah, I can't convert that. I just can't do that. And cast does the same thing. So we're going to show it the same kind of, I want to show preference. My preference is to convert, but a lot of people do use cast. And Microsoft said, okay, we're going to take pity on you. So we're going to give you this function called try convert. And there was a shout of joy from the universe in the data world, and everybody said, yes, thank you, thank you. But let's see what happens when we use that one. Well, we don't get any errors, but you'll notice now we're actually missing data. So it's a little bit better because we don't get that error, but we're now missing data because it can't convert it. It just sends a null. So, and then the same thing if we're going to use try cast, same thing. We're going to be missing data. So, and that's exactly what we have is garbage if we don't store the data in the correct data type. So if we come over here and we look at all of the distinct values for August 7th of 2015 and how they are stored in that character data type. Like this one even has a typo in it. So just something to be very mindful of is you still want to, even though you have those formats on the front end preventing people from entering bad data, you still have to store it in the correct data type. So that's dates. Let's take a look at integers. So I just have a very simple table right here. And I have the exact same data in each one. The first column, it's storing it as a character data. The second column is storing it as an integer. So let's see how this works. So looking at my list of numbers, let's look at the integer data type field and pick everything that's greater than 10. And we should get 8 records, and we do. I think we can all agree that all of those numbers are greater than 10. But what happens when we look at that varchar field and we say, let's find something greater than 10 there? Well, now, I mean, I'm not a rocket scientist, but I'm pretty sure, 2 through 9 are not greater than 10. Now, other people have said, yeah, but we're only putting numbers in there. So why did you compare that to a string value? Well, as a DBA, sometimes I'm not always certain what is being stored in a field. So if somebody says I'm storing it as a string, then I'm going to compare it to a string. In this case, I can see, hey, they're all numbers. Let's just go ahead and compare that character column to a number to see if we get the right answer. And lo and behold, we do get the right answer, but it comes at a cost. And we're going to talk about that when we get to the performance section of the session today. And let's see, one last thing I wanted to show you, sorting your data. So I just have that same data set, and let's go ahead and order that data by the integer. And sure enough, that's in ascending order. Yep, we're all good there. But what happens when we try and sort it by the character data field. Totally not consistent. It's sorting it based on the collation that you have installed on your server. So I have case insensitive, accent sensitive, 1252 installed on my machine. So that's how it's going to sort it. So you need to make sure that you really understand, if you want to be able to sort something, you think it's a number, but it's stored as a character string, it may not produce the results that you're looking for. So with that, let's get back to our slide deck and data quality. That's affected by your comparison operators, and it affects your sorting. If you're relying on data coming back in a specific order, you could be getting the incorrect result. So again, it doesn't matter how fast your query comes back if it's bringing back the wrong data. So just remember, if it's garbage in, it's probably going to be garbage out. You need to store it in the correct data type if you don't want your data quality to be affected. So with that, do we have any questions on data quality right now? I can kind of see the chat window here, and I know I'm not seeing anything, but I'm going to take this opportunity to give you guys a couple seconds to come up with any questions while I take a drink. All right, still no questions, so we're just going to keep on going. So storage is next. And they're just numbers, right? I mean, I can't tell you how many times I've heard that. It's just numbers. It doesn't really matter which one that we choose, what data type we choose. Well, maybe. So remember I said we were only going to talk about whole numbers today. So we have tiny ints, 1 byte, the range is 0 to 255. Small int, 2 bytes, negative 32,000, positive 32,000. So our range is getting bigger as we get larger in our data type size. We have integers, 4 bytes, negative billions to positive billions. And then we have big ints, which are 8 bytes, and that's like 6 commas. And I have no idea what that is called. I have million, billion, trillion. I don't know what comes after trillion. I'll never have that much money, so why should I know how to say it? Anyway, so let's just take a quick look via a demo to see if they really are just numbers. So I'm gonna come over here. We are done with this one. All right. So we've got our warehouse. It's that wide world importers. And there is a table called delivery methods. And it's not a very big table, and I copied it over into my demo database. And you can see we've only got 10 records here. So not a huge table, but they're storing their delivery method ID as an int. Well, so I want to show you the impact of when you store it in those different data types. So I created 4 different tables. I've got one that's storing it as a tiny int, one is a small int, one is an int, and one is a big int. So I wrote this cute little stored procedure so you guys wouldn't have to look at 20 lines of code, so I could produce this nice result set for you. And when we come in here and take a look at this, you can see I've got 67,000 records in each of these tables. They have the exact same data in each of these tables. I have my data space, how much index space is being used, add those together, you get the total in size. And the change in size and change of percent will come in once we start increasing the size of this data. So right off the bat, we can see that between a tiny int and a big int, it's about 500K. That's nothing. That's chump change when we're talking about today's storage abilities. So that's probably not that big of a deal. But everybody always wants their stuff to go faster. So let's add some non-clustered indexes on this stuff so it will go faster. And let's see how those indexes have affected the storage size. So now it's effectively just a little bit more than doubled our total size right here. And this was our percent increase. So it a little bit more than doubles just by adding that single non-clustered index. Okay, well, you're still thinking, okay, well, yeah, but still we're only, that's only a meg of data difference. Not that big of a deal. Well, you're right, but what happens if you have a huge table? And in this example, we're just going to say 10 million is huge. Let's compare these. So there's my 67,000. So this is my small table up here. This is my huge table down here. And now look at the difference in size from a tiny int to a big int. Now we're talking 70 meg difference. We don't have any indexes yet. So let's go out here and, of course, add some indexes and see how that affects it. And this takes it a couple of seconds to add those indexes on there. I need to find a loop for Jeopardy music to play while these are executing. I haven't found a good one yet, though. And for those of you who are not familiar, Jeopardy is a TV game show where they play music while people think of the answer to a question. Sorry, I forgot who my audience was here for a moment. It normally doesn't take that long. Okay, it finally came back. Sorry about that. So now let's go see how those sizes are affected. So if we zoom in here, and again, it's a little bit more than double in total size, and we can see our percent change. So it's still that 50%, but now that 50% is 140 meg of space that we're wasting to store the exact same data. So, things to think about on that. So let's get back to our slide deck. And they're not just numbers. You saw that, if you are in a data warehousing situation and that delivery method ID is going to be used billions of times and not just tens of millions of times, you can see how much space you would be wasting if you had sized it as a big int versus a tiny int. Now, and I often get this question from people, well, so you're telling us to always use the smallest data type. And no, that is not what I'm saying. What I'm really saying is you need to understand your data domain and then choose the most appropriate data type. So if you are going to store a person's age, for instance, that would be an appropriate data type would be a tiny int. I don't know anybody who is more than 250 years old that is living. And I also don't know anybody who's negative years old. So a tiny int would be appropriate if you wanted to store the age. We're not going to start the whole philosophical, well, just store the birth date and then you can calculate the age. Nope, I realize that. That's a whole other conversation. Just as an example, if you wanted to store age, a tiny int would be a very good solution as opposed to a big int, because a big int, nobody is ever going to be 6 commas worth of years old. So there we have it. Understand your data domain and then choose the most appropriate data type. That is what I'm advocating. All right, so let's talk about string data. It's just string data, who cares, right? Doesn't really make a difference. Well, maybe, maybe not. So let's take a look. For our string data, we have a character data type, and that is fixed length, and it will be the length of the actual data that's being stored. Then we have variable character. The difference between character and variable character is that variable character is only going to store the length of the data plus 2 bytes. So an example here is if I have a char 10 that's the one on the left-hand side, it's always going to take up 10 bytes of space, even if I only put 2 characters in there. But if I have a varchar 10 and I only put 2 characters in there, now it's going to use 4 bytes of space as opposed to the 10, because it's the length of the data, which is 2, plus 2, which is its overhead. So that's the difference between fixed length and variable length. So, and then you have the nchar, which is for Unicode. So basically anywhere outside the US probably needs to use the Unicode data types. These are 2 times the data length. You can have a max of up to 4,000 characters. And then same with the variable character, Unicode, you can go, it's 2 times the data length plus 2 for its overhead. So it's just string data. Let's take a look at our demo and see if it really is just string data. So we're done with our numbers. Let's come over here to our character data. And this time I'm going to look at the cities. I'm pulling in the cities from that wide world importers. And I'm, again, just like I did with the numbers, creating different tables and storing that city name with different data types. So one has a char 255, one has a varchar 255, and one is an nvarchar 255. So let's just take a look and see how that looks when we have kind of a smallish table, 37,000 records. Wow, look at the big difference in data size. That is almost 10 times as much, 1 meg versus 10 meg. And this is storing the exact same data. And again, we don't have any indexes assigned yet. And this is our total size. So let's go take a look and see what happens when we add an index, because, you know, everybody wants their stuff to go faster. So we have to add indexes. And these are just non-clustered indexes that I'm adding. And we can see, lo and behold, there's our index size. Again, it's just a little bit more than what our data space was. And when we look at the total difference now, holy cow, it's still 10 times as much data, but now we're talking about an 18 meg difference. So you can see where this is going. This is kind of big. It makes a really big difference. So let's take a look at our huge table to see what impact that has on it. So when we come over here and we look at this, again, huge is our 10 million record row. So yep, we've got over 10 million records. And look at this, our data alone, that's a 2.5 gig difference between our variable character, sorry, I lost the word there for a moment, versus the character data right here, the fixed length. So that's 2.5 gig difference right there, where we're wasting to store the exact same data. And again, you know, everybody wants their stuff to go faster. So we're going to add some indexes onto those, and we'll see how that impacts. Now, normally when I do this session in person, I ask the question, how many people think that this is going to follow the same pattern that we saw with the numbers, where it's going to be just that little bit more than double the size? And then people raise their hand. So in the chat, how many think it's going to be less than that little bit more than double? And you just type the word less or L or something, if anybody thinks it's going to be less. And then if you think it's going to be about the same, just type same. And if you think it's going to waste even more space, say more. So I can get a little bit of feedback here to see, make sure you guys are all still awake. I know it's the end of the day. It's been a long day. Everybody says it's going to, okay, so far everybody's saying it's going to take more than that little bit more than double. All right. It's still running. All right, it's finally done. Let's see what the answer is. Dun, dun, dun. And we zoom in over here and look at that. It's still just a little bit more than double. So it's following that same pattern that the numbers did. So here is our indexes. That's again, there's that 2.5 gig difference. And now when we look at the total size, we've got that 5 gig difference. So it's following that same pattern that the numbers did. It's just that little bit more than double. All right, so with that, let's get back to our slide deck really quick. So it's not just string data. Good examples of when to use fixed length versus variable length. In the US, we have social security numbers. It's like our national ID number, and it's 9 digits. It's always 9 digits. And you know, when somebody passes away, they have to wait so many years and then they'll reassign it. So they just cycle through them. So that would be a really good example of something to use fixed length. You could use a char9 for that. But because it's never 8 characters and it's never 10, it's always 9. But what about telephone numbers? Would you want to store that in a fixed length field or a variable length field? And here's where you need to understand your data domain. If you're in the US and you're only ever going to deal with US numbers, you could make that 10 digits, 10 characters, and you would be perfectly fine. But if you are going to store anything outside of the US, so if you're going to store international numbers, then that's not going to work because, you know, unfortunately, as most Americans think, the world revolves around us, and it doesn't. There's a whole big world out there. So you need to understand your data domain and then choose that data type correctly for your data domain. All right, last one, date. Dates are dates, right? Well, I think you guys get where I'm going with this. Let's see though. So we have a date. It has the accuracy of down to 1 day. We have a small date time that's accurate down to a minute. You can see we have different ranges for those values. We have date times, that's down to milliseconds. Again, a different range of values that are available. And a date time too, which is accurate to the 100 nanoseconds, which is like super accurate. And another, you know, a different range of dates that matches the date on the left-hand side there. So let's jump in and see if a date's a date. All right. So we're done with our characters. Let's take a look at our dates here. So again, I'm just using stuff from the wide world importers, pulling it over into my demo database. I've made 4 different copies of that table. One where it's storing that order date as a date, a small date time, a date time, and a date time too. So let's take a look and see how this affects. Whoa, my mouse has gone a little bit wonky there, sorry. So not a very big table, about 70,000 records, not a huge difference in data. We're talking maybe 300K between the date and the date time too. So not super big, 300K. But again, everybody wants their stuff to go faster. So we're gonna add some indexes on that. And let's see how that has affected our size. And over here, there we go. All right. It looks like, so here's our data over here. Here's our index over here. And again, it's just that little bit more than double. And now the difference between our date and our date time too is 600K. So still, you know, fairly insignificant. But again, that's just a small table. So let's look again at that huge table with 10 million records and see the difference there. So here is our huge tables down here at the bottom. We've got just over 10 million records. And our data space right here, we've got, let's do some quick math. 36 plus 16 is what? 50, 52, right? About 50 meg. We'll just call it 50 meg. So, you know, we got about a 50 meg difference there. Still not that big of a deal. And And again, yep, you know it, we're going to go add some indexes on there. And again, while those are churning, do you think the dates are going to follow the same pattern that we have been seeing with the numbers and with the character data so far? So less than that, more than that, or the same? What do you guys think? Use that chat window. Let me know what you guys think. Make sure everybody's still awake. No responses. I'm assuming I've put everybody to sleep at this point. I'm very sad. Really? Come on. Just one person. Let me know that you're out there. Okay, there we go. You're awake. All right. I'm just going to chalk that up to a delay from being so far away. Yeah, that's what we're going to call it. Okay. All right. So, well, let's take a look and see what that is. And now it's still that 30%, but now we're talking it. Now it's about 100. It's 100 meg. So not nearly as bad wasting space with dates as it was with character data, but we're still wasting space to store the exact same data. So let's get back to our slide deck. If I can find my mouse, there it is. Oh, all right. So as we all know, a date is not a date. Not all dates are created equal. So examples of things that could be stored as dates. Well, a birth date, that's an obvious one. Well, what if we are the Department of Motor Vehicles? Do you think the Department of Motor Vehicles cares what time I was born? Probably not. So if I was building a system for the Department of Motor Vehicles, I could store birth date as a date data type. I don't need a time associated with it. But what if I am the Office of Vital Statistics that is actually recording birth dates and times? Well, then I probably would want to use either a date time or a date time too. I don't think the Office of Vital Statistics really cares about 100 nanoseconds accuracy, so you could probably get away with a date time, but you have the option if you wanted to. Again, it comes down to understanding your data domain and then choosing correctly. All right, so not all dates are created equal. And when we compare them together, the big winner or loser in this case is the string data types. For when we talk about 10 million rows, storing the exact same data, that is the big loser. That's where we're going to lose the most space, is if we are using fixed length character data versus variable length character data when we can. So things to keep in mind. So that's it for the storage piece. So are there any questions out there on the storage piece before we move on to performance? And I'm going to take a quick drink right here while I wait to see if anybody has any questions. All right, no questions. All right, performance. That's what we're going to talk about now. Is it better to move to date time too? Well, let me ask you, what is your front end? Because there are some languages that don't support date time too. So that's another thing you have to take into consideration. Not all languages support a date time two data type. So not only do you have to understand your data domain, you also understand how downstream processes are going to be consuming that data and if it will be affected. Does that answer your question, Luca? Yes, no, maybe? Okay, well, I'm gonna keep going. All right, okay, there we go. All right, it must be the lag waiting for that to come through. So, all right, so performance. This is, I'm sure, what most everybody really wanted to see is the performance piece. So for performance, there are two different things we need to talk about. One is CPU, and the other one is disk speed. So when we talk about CPU, we're really talking about the execution plans. And execution plans are what SQL Server uses to figure out kind of the roadmap. It's the roadmap for the query engine to get you the best answer the fastest. So it's creating that map to get you that answer the fastest way possible. And when we talk about execution plans, we have to talk about searchability. So searchability, it stands for search argument. And what that really means is that we want to be able to use those indexes. Searchability means that that predicate can be executed using an index seek. It's just going to use our index. That's all that means. And our predicate is typically, you know, expression, operator expression. So let's look at some examples. So let's start with something that's not searchable. So we have this function right here. We're using a date add on a column, that function, and we're comparing it to a variable. Now, the reason this is not searchable is because it has to do that extra work on that column to get an answer. So it can't use the index. It has to do something first. So it's almost like it's creating a detour on your map to say, oh, I have to go out here. I have to do this date add. I've got the answer. Now I can come back and now I can keep going and I can compare it to that variable. So it's kind of like a little detour. Here's an example of something that is searchable. So we're comparing a column to a variable and these data types match exactly. So that's searchable. So you're going to get that straight line. It says, oh, yep, that column, I don't have to do anything to it. And here's this variable and it's the same data type. I don't have to do anything to it. Okay, now I can get you. So it's building that straight line on that roadmap. And we all know the shortest distance between 2 points is a straight line. And that's what we want to do. We want to be able to create that straightest line to get the best performance for our execution plan. Now, one thing we need to take into consideration is conversion precedence. So when we were talking about data quality earlier, I was able to compare a number to a string value and get the correct answer, but I told you it was going to come at a cost. Now we're going to talk about that cost, and that cost is called implicit data type conversion. So even though SQL Server, the engine is super smart, one thing it cannot do is it cannot directly compare two different data types. So one has to be converted to the other. And in order to do that, you have to follow the precedence. So here's the precedence for SQL Server and how it converts. And I always, when I look at this, I always get confused as to which takes higher priority. Is it the highest number or is it the lowest number? Well, here's how I think about it. A tiny int can always become a small int. A tiny int that's just 0 to 255. Whereas a small int, which is negative 32,000 to positive 32,000, it can't always become a tiny int because as soon as it's a negative number or it's 256, it can't be a tiny int. So it has to convert up. So the lower the number has the higher priority. Does that make sense? I'm hoping that makes sense. Okay, so let's talk about, or let's just jump into a demo and look at the performance for those execution plans. So let me bring up, all right, we are done with that. Let's come over to our searchability and we are going to make sure that I have done everything. We're in the right database. Let's set our statistics time on. Oh, I need to come over here and start a workload. So I have kind of a big beefy box that I'm running on. So I want to make it look like it's a big busy box. So I'm just going to start this in the background and have this running. All right. And here's what we're going to do. We are going to compare, in this query, we're going to compare our delivery date method ID. And as you can see, it's an integer. And we're going to compare it to a variable, which was declared as an integer. We're going to see how that affects our execution plan. So we're going to free up the cache, make sure there's nothing in there, and see how this behaves. So when I do that, we get this answer back, and we look, and our CPU is pretty negligible. And when we look at our execution plan, I'm going to hover over this and I'm going to have to zoom so y'all can see it. All right. We come over here and we look at our estimated CPU cost. Pretty negligible. Here's our predicate down here. It's doing a seek, so it's using that index. We're all good. CPU is good. We're fine. Okay. Well, let's take a look at what happens when we compare a column that is a character data type to a variable that is an integer data type. So we're going to do the same thing. And let's come and look at our CPU over here. It's kind of funky depending on how it hits that cycle in my workload. So it actually looks like it went faster, but let's take a look at the execution plan to see over here. And here's our CPU cost, and look at that. It's actually exponentially slower. Now, because the CPU cost is so small right now, we're not noticing it. But that is exponentially slower. Before it was 0.009. Now we're at 0.07. Okay. And then if we look down here, we can also see our predicate is now been bumped up to the top. And here's that convert implicit function that I was talking about. So that's where that extra CPU comes in, is that it says, oh, hey, wait a second, I can't compare a character to a number. I got to convert one of those. So it does the conversion and then it compares them, and that's where your cost comes in. And let's take a look. And that was a small table, so let's see what it looks like when we are looking at a big table. So let's come over here. So this one, it's about 16 milliseconds. And again, let's look at our execution plan. And here's our CPU cost. Well, we would expect CPU to go up because now we're looking at, like 10 million records as opposed to 67,000 or whatever we were before. And because, again, we are comparing the same data types, our predicate is down here at the bottom. There's no convert implicit. It's not too bad, 1.38 for estimated CPU cost. Well, let's look at when we do that, comparing a character data type to an integer data type on that large table and see what happens. So we're going to pull this up over here and you'll notice our CPU time. Wow, that is significantly more than it was before when we were comparing the same data types. And look at this, when we look at our execution plan, our CPU cost, that's like double CPU. And again, our predicate, they've had to add that convert implicit because it can't compare those two different data types. So we're wasting CPU cycles. And you might be thinking, well, yeah, but that's just milliseconds. Who cares? That's not a big deal. Well, what happens if you have a query that executes hundreds or even thousands of times an hour or a minute? You are wasting CPU cycles. It's going to have an impact and you will notice it. So just keep that in mind. All right. And that is performance execution plans. So think of implicit data type conversions as detours. Remember, it says, oh, yep, I can't compare those two. They're not the same. I have to go around, convert it. Okay, now I can keep going. And then your table and your index scans, those are construction zones. So if it's not sargeable, it can't use that index and it's just going to slow it down. So that's how I compare those two things together. All right. Last thing on performance is our disk speed. That's our input output. So there is this notion called a fat table. And a fat table is something when we add up all the lengths of all of the columns in our table and it exceeds a certain amount. So SQL Server stores data in 8K pages. What I've done in my example is I have this supplier table. It's got 36 columns in it It's using all of the correct data types. And when you add those values up, it adds up to about 2,000 bytes for an entire row. Then I created my fat table. It's got those same 36 columns, but now all of those data types that I can convert to a that were character before, I'm now changing them to char 255. And when I do that, my max length now is going to be about 6,000 bytes. And remember, SQL Server stores stuff in 8K pages. So it's going to take us an entire row to store one record in our fat table, as opposed to our original table. We could possibly get, you know, a minimum of 4 if we had the max values in there, if they were all maxed out. You get where I'm going with that. So let's just jump into the example. It's a lot easier to see than me trying to explain it to you. So let's take a look at this over here. Let me stop that workload. All right. So I have to dumb down my machine a little bit here so you guys can see all the differences that we're going to talk about. And let's go through and let me just do a little bit of cleanup to make sure that I cleaned everything up from when I was testing my demo earlier today. All right, so we've got our 2 different tables. They each have 10 records in them. It's the exact same data in each of those tables. You can see, just looking at these here, it's the exact same stuff. And let's compare the sizes. Let's see how much space they're actually using. And when we zoom in a bit over here, our original table, it's using 8K, whereas our fat table is using 80K. That makes sense because it's got 10 pages, 8K per page. That's 80 kilobytes right here. But with our other one, because we're using variable character data there, it's not using all of that. It's only using what it needs. And right now, it's still just at 8K. It's just on one page, at or under 8K. So let's come over here. And there's this great DBCC option that you can use that will show you how many data pages are being used. So if we look at the original table, anything that has a number 1 as its page type is a data page. So we've got our header record and 1 data page. So we're storing all 10 of those records on a single page. Let's go back and look and see what happens for our fat table. And again, we've got 11 records, one of which is our header, and it is indeed 1 page per record. That makes sense because they're 6K each because it's fixed length. So what does that really mean? Well, let's see this in action. Let's add a row, a small row. So I'm just picking the number 15 and I'm adding the letters ABC where they're character, and I'm doing that to both the fat table and the original table. Let's execute that. And let's come up over here. And you can see there is that additional row that I have added. So how is this going to affect the number of pages? Well, what do you think about the first one? Do you think we're going to have more pages, or are we still just going to have that 1 data page? And then when we look at the fat table, do you think we're going to have 1 more page, or are we still going to be at that 10-page level? So let's go and look. Let's investigate and see. So here is our original table. And lo and behold, we still only have 1 data page. And when we look at our fat table, we now have, zoom in over here so you can see, we've got 12 records. Again, only 1 of them is the header. So it took, again, that entire page to store that 1 record. You're thinking, okay, well, that's super interesting, Angela. Wow. Well, how does that really affect me? Well, let's stop and think about this. What happens if we have something with a lot of data in it? So here's my super big table. It's only got 100,000 records in it. And when we look at this, we can see it's easier if we come over here, 6671. One of those is a header record. So 6,670 pages is what we have to store 100,000 records in our regular size table. Well, what happens at our fat table? How many pages does it take to store 100,000 records? Well, let's go see. And it's still churning, it's still churning, it's still thinking about trying to figure out how many pages there are. It's still going, okay, it's finally done. Let's take a look. Look at that. 110,000 pages to store that data. That's a lot of pages. Well, what does that really mean? Well, let's take a look first. How much space is that using when we compare those together? So we've got basically 800 meg difference, a little bit more than an 800 meg difference because we have to store all of those additional pages. But more importantly, so here's what I'm going to do. I'm going to set my statistics IO on. We want to see how this affects our IO. How many times are we going to disk? How does that affect it? And I'm going to turn this trace flag on. What this trace flag does is it disables read aheads for sequential reads. Do not turn this on in your production environment. What this is basically doing is it's forcing the query to go to the disk for each fetch. So it's totally bypassing anything that's in cache. It says, nope, I ignore cache completely, go out to disk for every single piece of data that I need. That's what this trace flag does. Do not put this in production systems. This is simply for demo purposes. So let's make sure we don't have anything in our buffers. All right, and now let's just look at our big table and just do a simple select where our supplier is 15. Let's execute that. It's done. Let's come over here. So we are doing one scan count. So it's looking at our table one time. It's doing 6,600 logical reads. That's the number of pages that we have. So it had to go out 6,670 times to disk to do physical reads. Well, let's look at what happens with our big fat table. Again, let's make sure there's nothing in the buffer and pull this up. And it's executing, and it's executing, and it's still executing, and it's finally done. And we come over here and look at that. Again, it's looking at our table one time. Logical reads, 110,000. Physical reads, 110,000. It has to go out to disk 110,000 times. What happens if you are using old spinning rust? If you don't have SSDs, if you have old storage, that is a huge, huge impact. So, numbers kind of speak for it right there. So let's get back to our slide deck because we've only got about a minute left. More pages means more IO. That's what that means. That's what we're talking about. More pages means more IO. And now I know some of you are saying, well, I use in-memory tables, so that's not really going to affect me. Well, wrong. For memory optimized stuff, more pages means more memory that you will be consuming. So it does affect you. And that is it for performance. And we're kind of at the end. Biggest takeaway from today, understand your data and choose the correct data type. And that's all I have. I do have some great resource information on my slide deck that that'll get posted. Here's how you want, if you want to connect to me, you can. The only thing I ask is that if you reach out on LinkedIn to connect on LinkedIn, I'm happy to do that, but just tell me where you saw me because being a woman in IT, is a little sketchy on the internet at times. So if I don't know who you are, I'm probably just going to ignore you unless you tell me where you saw me. And that is all I have. There are some great links to some performance stuff for reference in here. But that's all I have. And I'm done.